Sorry, I had to fix those typos right there. Let me write out explicitly what that is. This is 1/2 mv squared, but we know v is equal to r times omega. So this is supposed to be omega here. So this is going to be 1/2 m, where the v is r omega. That would be r squared omega squared. That's what this is supposed to read. It's difficult to read there. And we recognize this as the moment of inertia. So it's going to be right here is the moment of inertia, mr squared. So this is going to be 1/2 times the moment of inertia times omega squared. And if you look at this, you'll notice it's exactly comparable to what we have in the situation of the translations. We have 1/2 times the mass term times the velocity term squared. So let's write that out explicitly. Kinetic energy rotational is equal to 1/2 I omega squared. That, of course, is incredibly important. So that baseball that's thrown has two kinds of energy. It has a kinetic energy due to translation and a kinetic energy due to its spinning or rotation. So the full kinetic energy of the object is going to be 1/2 mv squared, where v is the velocity of the center of mass. In other words, the motion of the thing as a whole, plus 1/2 I omega squared, where this is the moment of inertia around the center of mass, probably at something very close to a sphere, times how fast it's spinning. Even when you throw it up, at that moment when it stops in its upward climb, it's going to have a kinetic energy due to its rotation that keeps spinning. So this would be the full kinetic energy, and if you were going to do a conservation of energy problem, you would take this plus the potential energy to work a more complicated problem, like the energy of a rotating object when it's going down a hill. Now that's a good one to work at this point rather than in the last section. So we're going to work now a problem where we look at something that's rolling down a hill. And I'm going to, in this case, take, first of all, let's take a cylinder. You call a cylinder is 1/2 m times r squared. That gives us the moment of inertia of a cylinder. So I'm going to look at a cylinder sitting here. We're going to take this cylinder at a certain height, h. We're going to let it have a certain radius r. And we're going to let it roll down this inclined plane till it gets to the bottom. It's going to roll down with an angle theta. So, but do we really need this angle? Well, let's stop and think about it. Do we know, if it has a mass m, what the potential energy is up here when it's stationary before we release it? The answer is energy before, energy initially, is going to be equal to the energy finally. And the energy initially is going to be equal to the kinetic plus the potential. But it's not moving, so we have no kinetic energy. So the energy initially is going to be m times g times h. That's actually a capital M times g times h. That will have to equal to the energy that it has at the bottom. When the cylinder gets to the bottom, it has no potential energy. It's already exhausted its height. So relative to here, it has no potential, but it has kinetic. Two kinds of kinetic. So this is different from having a mass just slide down a hill when we would have 1/2 mv squared. And if we did that, if this just slid down the hill and did not rotate, we could immediately compute v as the square root of, the mass cancels, of course, the square root of 2gh. But now we can't do that. We have plus 1/2 of I times omega squared. So we need to work this out and see what we get. We have 1/2 m times the velocity squared plus 1/2 Now our cylinder is going to be 1/2 mr squared. And our omega, you recall that the velocity is equal to r omega. So omega is equal to v over r. And so this is going to be v squared over r squared. And the reason for that is we're assuming it rolls without slipping. And you recall previously we looked at the fact that if something is traveling in this direction with a velocity v, then its tangential velocity for rotation was v in the opposite direction, which gave us the relationship between the tangential velocity and the angular velocity. Now we can cancel the two r squareds, and what we end up with is 1/2 mv squared plus 1/2 times 1/2, 1/4 times mv squared, which is 3/4 mv squared. That tells us that the velocity is going to be very different from what we would have had before. Here the m will cancel again, but we're going to have 4 times gh divided by 3 and the square root of that. So if we compute this velocity, we would have 3/4 mv squared is equal to mgh. And now the m's cancel, and our velocity is going to be equal to 4gh over 3 square root. Of course, the 4, we could get a 2 that comes out of that, but this is obviously different from the square root of 2gh, which we had before. If we have other objects, you can also compute what they would have, and let me leave this as a homework exercise, to take not just the cylinder, but to take a sphere, or to take a ring, or to take another object, and let it roll down the hill and see what velocity we would get at the bottom. In fact, the one moment of inertia that everyone should be able to get immediately is if I have a hollow ring where all of the mass is out here at the edge, then the formula for the moment of inertia, which is mr squared, is simply this mass out here divided times r squared. And so it's simply all the mass is the same distance, so it's very easy to compute. So this is the moment of inertia of a ring, which is the same as having one point out here at a fixed distance. The rest of them are they have some kind of coefficient times mr squared. Perhaps the simplest is where you have a cylinder. So if I took that mass and made it solid over this cylinder, and you had a round cylinder, then you get a factor of 1/2 because much of the mass is closer to the center. Therefore, it's not quite as large. Therefore, it's easier to turn an object that's solid like this than an object where it's all out at the edge. For example, a bicycle wheel. It's all out at the edge of the bicycle wheel.